right, so we're going to start with talking about converting minutes and seconds into degrees. I will say in advance that your book actually has you do both directions. It talks about how you turn in minutes and seconds into degrees, and it also talks about how you turn decimal points of degrees back into minutes and seconds. I'm not going to teach that part of it because in practicality, it's not all that useful. The reality is that your calculators do decimals just fine, and it doesn't matter if you have decimal points of degrees. But it is useful to be able to take something like this as an example 1, and it tells you it's 41 degrees, 24, that first hash mark means minutes, and then the 3 and the second hash mark right there means seconds. Well, I need to be able to take that value right there and turn it into a decimal to be able to use it easily within my calculator environment. Okay? Some of your calculators have the ability to deal with the minutes and seconds without converting them. Not all of them do. And it's easier to work with them in decimal points of a degree. So that's the first thing we're going to talk about is how to convert those. All right, so we're going to take a look today at converting these minutes and seconds into degrees. So the first thing that you want to know is what these are. So 1 minute is equal to 1/60th of a degree. And maybe an easier way to think about that is to say it like this. 60 minutes, not the TV show, 60 minutes. Do you guys even know what I'm talking about when I say that, or is that before your time? Is 60 minutes still on? Oh, okay, that's good. All right, so 60 minutes is the same thing as 1 degree. So it's kind of like having, you know what, let's do it like this. It's kind of like having 60 minutes equals an hour. That's kind of the relationship you should be thinking about, all right? And it works the same way for seconds, except that seconds is even better because it works exactly like it does with minutes on a clock, all right? So 1 second is 1/60th of a minute. Or likewise, 60 seconds is equal to 1 minute. Okay? So if you think about what a degree is a very small sliver of a angle measure, right? 1 degree is very small. If you were to partition it down into smaller increments, those would be the minutes and seconds that we're talking about. Now, conversion for them is actually really very, very clean. So we have 41 degrees, we have 24 minutes, and we have 3 seconds. The way that we take that and we turn that into a degree is we have our 41. 24 minutes, well, that's 24/60ths of a degree, right? So this is 24/60. Now, the other one is a little bit trickier to look at. This is 3/60ths of a minute, but I want it in degrees. So what we actually do is we take 3 over, and I'm going to write it this way just so that I can talk about what it's doing, 60 squared. You could equivalently write that instead of writing it as 60 squared, write it as 3,600 here instead. Okay? So 60 squared is 3,600. So why did I get 60 squared? Well, I had to put it over 60 one time to turn it into minutes, right, because it was in seconds. And I have to put it over 60 again to turn it into degrees. So that's why the 60 is there twice, so we have 60 squared. So grab your calculator if you have it with you, and I really hope you do, because you need to be bringing it each day. You'll use it almost every day in this particular class. That's not true about every class you're in, but you'll use it very, very frequently. So grab your calculator, and I want you to find out for me what is 41 plus 24 divided by 60 plus 3 divided by 3,600. Okay? And it tells us we want it accurate to 2 decimal places. Okay? If you don't have a calculator today, it's okay, just bring it next time. So it'll be 41, and then it'll be a decimal point. And I know that much of it because it's 41 degrees, and everything else is a portion of a degree. So it can't add up to make this more than 41. Yes?
Does it matter what mode?
It doesn't matter for the moment what mode. We'll talk about modes in a little bit, but it won't make any difference for what we're doing right now. Yeah. 0.40. And then we want to make sure that we put the degree marker on there. And I appreciate how you said that, the 40. It's not just 0.4, right? This said we want it accurate to 2 decimal places, which means we really need to write down 2 decimal places, even if the second one's 0, okay? So we will express that 0 as a portion of what we've got going on. So here's your calculator caution. And so remind me your name. Aaron. So Aaron's question of degrees or of the mode you have in your calculator, that's the calculator caution. So you were right on target for where we're headed. There are 2 modes in most of your calculators. So one of those modes is called degree mode. And then the other one is called radians. Now, we haven't actually talked about radians, but you need to make sure you're using the right one at the right time. Now, her question about the last one, it didn't, and I said it didn't affect that, was because we were just adding regular numbers together. Now, it will affect things when we start taking sines and cosines and things of angle measures. Once our value represents an angle measure inside of a trig function, that's when it'll matter. Okay? So we'll talk about the mode a little bit more, but I need you to be aware that there are 2 modes in your calculator, and it does matter which one you're in. Okay? So we're going to put this note in here. Be sure you are using the right one. All right, so we're going to talk about radians. And in talking about radians, we need to talk about what a central angle is and what a radian is altogether. Okay? So to start with, a central angle, there are 2, a positive angle where, whose vertex is at the center of a circle. Now, a lot of times we think of that as being at the origin of our xy axis, and a lot of times it will be, but it doesn't actually have to be on an axis at all. Okay? So that's what a central angle is. And what I want to show you for radian is how we actually get this thing called radian. I know that when I usually teach radians, people don't like them. They want to work in degrees because you're more comfortable with them. You've been doing degrees since elementary school, right? You've been talking about 90-degree angles and acute angles and things like that since a long time. And your reference for them all has to do with degrees. So this whole idea of radians and why in the world we need them seems a little obscure. Can't I just do what I already did before? And the answer is actually no. And the reason for the answer being no is because radians don't work with calculus. And trig is preparing many of you to go on to a calculus course. So we need those radians to be able to work in calculus. Okay? So what is a radian? Well, if you take and look at it this way, this is how we're going to describe it. All right. The rays of the central angle intersect the arc of a circle. If the radius is equal to the length of the arc, we say the measure of the angle, or the angle measure, let's go with that. The angle measure is 1 radian. All a radian is a number. So if you were to imagine taking a circle, let's see if I can draw one for you. Let's see if I left it. I didn't. So if I were to take a circle, and draw a circle well up here, and I were to take the central angle, which would look something like the radius coming out here, and another measure right here. And if, in fact, the length right here is equal to the length right here, that's what this is describing, then we call this angle measure right here 1 radian. And of course, just like degrees, right, you don't have to have a whole number. All right? I don't have to have a whole number of radians. I can have half of a radian. It would just be a smaller angle measure. Okay? It would be exactly an angle measure where the radius was twice as long as the length of that arc. That's what we would have. Okay, so it's a way of measuring. So imagine taking a tape measure and actually measuring the length around a CD, right? You guys still know what CDs are, right? Okay. So a CD, if you measured along the outside of a CD, that would be how we were establishing this relationship. Okay? The measure of the arc's relationship to the measure of the radius of the circle that you're dealing with. Now, we definitely want to be able to convert back and forth, because until you're more comfortable with radians, it's often easier for you to go back into degrees just to think about how much we're talking about here. And eventually, it's going to be useful to you to go from degrees into radians when you get to calculus, because you're not going to be able to do calculus with degrees. So we need to be able to convert back and forth. So the first one we're going to do is conversion of degrees into radians. And we're doing in this order simply because your book has the questions structured in this order is all the reason. It doesn't make any difference. But the first thing that you want to know is that you want to remember or know, in case you haven't seen before, that 180 degrees is the same as pi radians. That measurement is equal. So because that measurement is equal, we can create fractions with those measurements. It's kind of like saying 12 inches equals 1 foot, right? So if you're converting between feet and inches, we often write a ratio of 12 inches over 1 foot or 1 foot over 12 inches. Nod your head if you know what I'm talking about. Okay, so we're going to do the same kind of thing here. And we're going to write our fraction. So let me write what I've just said. Our fraction we're going to write is pi radians. And you can write the word rad for radians. Often, if you don't see the word radians written, that's okay too, actually, because a radian is just a real number. But if you write it, it will sort of jog your mind and remind you that's what you're working in. So we can write this as a fraction, pi radians over 180 degrees. This is a ratio of 1, because they're equal to one another. Thus, we can multiply by pi over 180 degrees. And that will convert degrees into radians. Now there's a couple of different directions for how that can happen. One of them is what we've got written here. We're going to convert the angle from degrees into radians, and we're going to leave the answer as a multiple of pi. So let me show you what that looks like first. So as we said, we're going to multiply, and we're going to multiply by pi radians over 180 degrees. And again, you don't have to write the rad part or the radians part when you're doing this. You can if it helps you. And what I want you to see is the reason for this relationship having radians on top of degrees is because the degrees are going to cancel. I've got a degree marker here, and I've got a degree marker in the denominator here, so those are actually able to cancel each other out. Make sense? So that's actually how you can make the decision. You don't have to memorize this rule. There is absolutely no reason for doing that. I need to put the degrees on bottom because that's the only way I'm going to cancel the degrees out. Okay? All right, so taking a look at this then, I actually can take my calculator, and you can take yours right now, and I want you to take 315, and you notice you're going to divide it by 180. We can ignore the pi for the moment, and I'll show you why, but we want to take 315 and divide by 180, and whatever you get is going to probably be a decimal in this particular situation. I want you to take that decimal and turn it back into a fraction. Almost all your calculators probably have that feature. If you're not sure where that feature is, flag me here at the end, and I'll look for it for you on your particular calculator, okay? But in fractional form, what is 315 divided by 180? Okay, so let's write it as an improper fraction even. 7/4, right? So we're going to have 7 and 4, and you're exactly right, it is negative because it was negative to start with. And notice I haven't dealt with the pi yet, so the pi is still there. So we would express this as 7 pi over 4. Excuse me, let me say negative 7 pi over 4. And that is equivalent to negative 315 degrees. Any questions on that? All right. Notice the directions on the next one are not the same. The directions on the second example here, which is example number 3, or I think it's supposed to be 5. No, it is 3. I'm sorry, I'm flipping my pages too fast. Is we're going to actually write our answer in decimal form with a rounded decimal value, or sorry, a rounded radian value. It says rounded to 2 decimal places, right? It doesn't say leave my answer as a multiple of pi. All right, so what that means is I start out the same. None of the original stuff is different. I'm going to multiply by pi radians over 180 degrees. So you're going to take your calculator, you're going to do 264.9, you're going to divide by 180, and it's going to give you some decimal, right? So can you tell me what that decimal is? You can give me several decimals at this point. I'm not rounding anything yet. So let's go with maybe 4 decimals for the moment. What do you have? 1.4716. Right. And at the moment, I still haven't done anything with the pi, right? Yeah? Okay, so in your calculator, you've got some decimal that looks like 1.4716, and it maybe has some more decimal points after that. Probably so. I want you to hit your times pi. Okay, we're actually going to take the pi out of the situation because it didn't say leave your answer with a pi in it. It said round it to a decimal, which means pi, which is a number, which is roughly what? 3.14, or you may know a 22 over 7 ratio as a ratio. It's roughly those. Use the pi in the calculator. Do not type your calculator ever in this course 3.14. It's never going to happen. There's a pi in your calculator, and we're going to use it. Okay? So if I take this decimal expansion, even with more decimal points than I wrote down, and I multiply by pi, that's the answer I'm going to write down. And I'm going to write that answer down accurate to 2 decimal places because that's the directions. So whatever the question tells you on decimal places, that's what you're going to follow. So what is that value then after you multiply by pi?
4.62.
Okay, you can leave it as 4.62. If it bothers you because it doesn't have any units on there, this is radians, so write radians after it if you'd like. If you don't have them written there, that's okay. And that brings me to a good point that I want to point out here. If you don't write units on something, it is assumed by default that the units are radians, okay? Which means that if it's in degrees, you have to write the degree marker. If it's in radians, you don't have to. That's just the way it goes. So keep that in mind as you're working. Now, we also want to go the other direction, especially for now, because you may feel more comfortable working in degrees, and you may feel more comfortable working in degrees for the entire time you're in mathematics. That's a possibility. But for now, especially, you probably feel more comfortable working in degrees. So we want to be able to take the radians and turn it into degrees. And again, it isn't changed. It's still the fact that 180 degrees is equal to pi radians. So before, we multiplied by pi over 180 to turn degrees into radians. So how are we going to turn radians into degrees?
180 over pi.
Right, we're going to multiply by the reciprocal of that, right? So we're going to multiply by 180 degrees over pi radians. And if you take a look down below, we have an example, 2 pi over 3. All right, so we're going to just get right on started with that. We've got 180 degrees. I've got pi radians on bottom. And you'll notice then, of course, that what happens to my pi? They cancel out. How nice was that? I don't have to use the pi button now. So in your calculator, you'll take 2 times 180, and then you'll divide by 3. Or you can take 2 divided by 3 and then multiply that by 180. It doesn't make any difference. No matter which order you do it in, what do you get? 120 what? Degrees. So when we're writing that, we need to make sure we have the degree marker on that. 120 degrees. Any questions? What is different about number 5 than was number 4? There's no pi. And that's actually the reason that the directions look somewhat different as well. The directions say express your answer in decimal form rounded to 2 decimal places. You're going to get a decimal on this one. So we're going to end up with decimal points worth of a degree. But the directions don't change the process. So the process is still multiplying by what? 180 degrees over pi radians. And you don't cancel out any pi's because there aren't any pi's in the 2 to cancel. So you're just taking your calculator and you're going to multiply 2 times 180. And then you hit the division key and divide by pi. The answer you report will have 2 decimal points of accuracy because the directions said so. And what do you get? Point what? 59 degrees. Very good. Don't forget the degrees. So it really isn't any harder if the pi's don't cancel, right? It just ends up not looking as pretty of a number. I get decimals in my number instead. So it's no big deal. Now we mentioned arc length just a minute ago, and I didn't actually ever define it. So arc length is going to be something we're going to take a look at right here. And I drew a picture for you earlier. I'm going to draw it again. So if I have a circle and I have a radius in my circle out like so, then the arc length is the length along an arc of the circle. So let me write a description for us before we do any more of my picture. So for a circle, with radius r, and central angle theta. Now we talked about central angle just a moment ago. It's the angle in the middle of the circle. Theta we talked about as a Greek letter we're going to use to represent our angles mostly in Greek letters. Then the arc length which is denoted with an S, is the arc intersected by the rays forming the angle, or the central angle if you want to be real specific. It's the only angle we've mentioned, so I'm going to call it just the angle. So in my picture, if I have those two relative to the distance traveled, S, in a given time t. Now, the equation that it just described was v equals s over t. You need to be careful the s was not speed. Speed is v. Do you know why they call v the speed here? Velocity. It's velocity. Good. So we're talking about the velocity, which is also another word for speed. And then the s here is arc length, because we already used it for arc length, right? So the length of the arc. And then t is time. And you might think, well, what other kind of speed is there? I mean, what is the difference we're talking about here? So let me describe angular speed and then try and describe how they're different from one another. So angular speed is the speed w of an object moving around a circle. Okay, so far it's the same description. Relative to the angle measure traveled. And that's theta. Again, in radians, no surprise there, right? And time t. And this one looks very similar. It's a w, it's actually the Greek letter omega. It's omega equals theta over t. So imagine a bicycle tire or a car tire, all right? And you put a nail in it. That's a not good thing, right? It means you're going to be taking a trip to somewhere to get it fixed at some point, which is the bad part. Well, that nail has two different speeds it's going, right? One speed is the speed that your car's going, and that's related to the distance that you've traveled, okay? How far your car actually goes. The other speed that it's going is the speed in relationship to how fast around the tires it goes. Now, it's easier to think about it in terms of a bicycle, because on a bicycle, you actually, at least many bicycles, have speed control, right? Like think of a 10-speed bike. That's sort of the description, right? You can change the speed or how fast you have to pedal to make the bike move, yeah? And if you increase the level that you're on, or I'm not sure the language I'm wanting to use, but you can actually pedal slower, but you can make more progress, right? And then when you get to the big hill, you have to change that so that you can pedal slower and actually get up the hill and not fall over. So that's the idea here. There's two speeds. There's a speed that it's going around on the tire, and then there's a speed along the ground that it's actually moving. And that's the two different speeds that this is talking about. So note, we can also combine these equations. So combining these equations, we can also see that the velocity, right, that's the speed along the ground that it's going relative to how far you traveled in that car, is equal to the radius times omega, which is the speed of the actual tire's movement. Okay. You might also be thinking of RPMs. So if you work on a stationary bike, sometimes it'll tell you your RPMs that you're going, right? That's revolutions per minute. That's how fast your feet are spinning around. That's kind of the same idea. It's measured a little bit differently, but it's the same idea. All right, so we're going to take one example of this, and then we'll be finished for today, and we'll talk a little bit before we head out just a second. But let's take a look at this. So we have the diameter of a wheel of a bicycle is 26 inches. If you're traveling at a speed of 35 miles per hour, which first of all would be really fast for a bicycle, okay, that's really, really fast. Through how many revolutions per minute are the wheels turning? Okay, so that's the revolutions per minute that I just brought up a minute ago. Okay, so the first thing I want to ask you is what is the radius?
13.
Right. So we haven't said that, but diameter is twice a radius. Okay, so that's something you should remember from geometry. So the radius is actually 13 inches here, so that's something we want to make note of and be careful we don't make a mistake on thinking about that. What is this 35? Is that the velocity, right?
Yes.
Yeah, that's the velocity, right? That's how far along the ground that you're traveling. So that's V. So my V is 35. And we're going to do some conversions here before we get any too much further. This is miles per hour. And what I want you to notice is that I've got one unit measurement of length in miles here, and I've got another unit measurement of length in inches. And the other thing is that I've got 2 units of time described here. This is talking about per minute, and this says hours. I can't have 2 units of measurement of time and 2 units of measurement of distance going on in the same problem. I've got to reconcile that. And the way I'm going to reconcile that is I'm going to turn my miles into inches, and I'm going to turn my hours into minutes. So I'm going to start with the miles. Does anybody know how many feet are in a mile?
5,200 feet.
Excellent, good job. All right, so 1 mile, and again I'm putting miles on bottom because I want that mile unit to cancel out with the mile unit that I have above in the 35 miles. So this is 5280 feet. Now I'm still not exactly where I want to go. Now I'm in feet. But I can turn my feet into inches fairly quickly because 1 foot is how many inches? 12 inches. Good. Now I have taken, in essence, and I've canceled out miles and I've canceled out feet. So now I am in inches per hour. Still not exactly where I want to be. I want to be in inches per minute because that actually talked about minutes earlier. So I can take this and now I'm going to actually do my 1 hour on top. So I'm putting my 1 hour on top because I need it to cancel with the hour that's on bottom over here, right? And how many minutes are in an hour? 60 minutes. So what this is going to do is it's going to turn my speed of my bicycle into inches per minute instead of miles per hour. And it's going to be a really large number by comparison to the 35. So grab your calculator. I want you to multiply 35 times 5280 times 12, all the way across the top. And then you'll divide by 60 at the very end. Okay? And what do we get for our velocity?
3,080.
What, did we get anything else?
I got,
Okay, that's what I have. Check your calculation one more time. Okay, so I also have 36,960, which is a lot bigger than the number 35, but it's now in inches per minute, right? Okay, so and I'm still not quite where I need to be, and one of the reasons I kind of know that is because I haven't done anything yet with that 13 inches, right? And that has something to do with what's going on. So let's take a look. We have this equation that we had established before, and that's a previous slide actually, that the velocity is equal to r omega. Because what does it ask me to find? It's actually asking me to find the revolutions per minute. Well, revolutions per minute is related to angular speed, not linear speed. Right? How quickly you're going around something is the revolution. So I need to get this in terms of angular velocity. That's the omega, the W letter that looks like a W there. So actually I have a relationship, and I've got the R, that's the 13, and I've got the velocity, which was the 36,960 that we just got from before. Let's see if I did that. Well, we'll just use a clean slate over here and go with that. So my velocity equals R omega. My velocity was 36,960, and the radius was 13. Right? So how do I solve for omega? Divide by 13. So what is my angular velocity?
I got 2,843.10.
Did you say 1, 1, 0?
Yeah, I rounded. It was 0.07.
Okay, let's go with 0.7 just for now. Okay. So, sorry, this is a little bit different than direction than I had intended to go. Let me pause just a sec. Okay, so this is revolutions. Okay, here's what we're going to do. I realize that it's 9:52, and I'm sorry about that, so let's pause this.